Honesty, and then specifically about models that we all use, but we got to remember their limitations. Honesty is a very fundamental scientific principle. We've got the quotes from MMSA, also by the bottom is the American Geosciences Institute's guidelines, some of their things. Everybody's got something about honesty in their codes. They say it slightly differently, but everybody seems to recognize it. And of course, lying is one of the big no-nos, and some examples we have. This water supply paper that, to its credit, the USGS, when they realized that the data in this paper had been faked, they went, sent out a notice to all the people they routinely send all their publications to, and the world in general, saying, if you have a copy of this document, destroy it. It's bad. I mean, it's a difficult pill to swallow in a way, but it's to their credit that they did it. And then, of course, mining and oil and gas frauds have been around since the industries have been. Gatorade Metallica, of course, has some nice things to say about stock frauds and watching out for them. We know about REACs. The oil and gas stuff led the American Association of Petroleum Geologists to adopt an ethics code in 1924. They were the first geoscience organization to do so. In fact, most of the organizations didn't adopt an ethics code if they hadn't one until the 90s, certainly after 1950. Some of them, because the organizations aren't that old, but anyways. Then there was this case of Intertech was a lab in Texas that was doing air, soil, and water sample analyses. They were forgetting to, clean the equipment between runs, to calibrate the equipment and so forth. And they got caught because a few people actually were paying attention to their quality assurance, quality control programs, and were sending duplicate samples to other labs, and realizing that there was a problem. But the result of what they're thinking is, hundreds of thousands of sample analyses were voided because they were doing the analyses correctly. And then more recently, there was this mass spec operator at a survey here in Denver who was fudging the data and so forth, and I have not seen whether that case has been resolved. But again, I realized that any of the data this fellow produced was unreliable. So case history, we had, this is a good number of years ago, we had a AIPG certified geologist who was promoting some mining claims in California, and he told investors he had reserves. Well, some of these claims were in the California counties that have an ad valorem property tax on reserves. And so he told the counties that they didn't have any reserves. He didn't want to pay any taxes. So when we brought him up on the ethics charges, we concluded that he lied to one group or the other, and we didn't have to decide which. It was just simply, two black and whites, and made that simple. And we've actually gotten some of the data, and we're working with the New Mexico Attorney General's office so that when we came to our conclusion, we provided the New Mexico Attorney General with an expertized opinion as to this fellow's professional conduct. They brought a criminal case. The guy was ultimately convicted. Now, I suppose most of you have seen this dihydrogen monoxide slide before. All 12 bullet points are true. But the way they're presented, and the fact that most people don't bother to figure out what chemical, the formula for chemical names, even MPs have discovered, you don't get the joke until you realize it's water. And of course, all those things really are true about water. But, it's been passed around to various groups, and people say, oh, we got to get rid of this stuff. Now, this is one of my own examples. That's a gold particle. Then there are these spherical particles. It was from a heavy minerals concentrate on a sample I took out in Nevada. And I was out there because a fellow was promoting his placer deposit, and he said, oh, we've got this drill hole that goes to the deposit. Well, somebody tried to drill a water well fairly far down on the alluvial band. There's about 5 feet of casing sticking out of the ground. The cuttings around it. It also happens but he had this geologist go out and collect a sample of stuff, and the geologist looked at it before he sent it for assay, and his report to his client was gold and buckshot, which most people say, huh? Classic salting. Well, this is supposedly classic salting. Well, the truth of the matter is that it's every Nevadan has the right to go out and carry a gun and shoot at anything out in the woods or the desert, which is also a bird hunting area, so that's why there's a bunch of buckshot in there, and actually, some of that buckshot comes in different sizes. So the gold and the buckshot aren't really salting in the classic sense, but at least there really is a real picture of gold and buckshot. Okay, and then there's knowing what ain't so. You've all heard the phrase, and Mark Twain never wrote it. Maybe never said it. Because I want to say, okay, where did this come? It's the sort of thing that sounds like it comes from roughing it. But of course, anymore, everything that Mark Twain wrote, it's been digitized, and you can search for it. And if you search for the phrase on the net, well, you come up with something like this that says, no, it's not true, even though it's popularly believed. And so we have this comment by DeFreitas that we need to acknowledge what we don't know. What are our biases? We all have them. They're true of any property, any report like that. What are the uncertainties involved? Indeed, one of the things that's actually in Section 27A of the Securities Act is the safe harbor for forward-looking statements. And it's an interesting safe harbor. First of all, it says you have to label forward-looking statements to protect yourself against attorneys' clients' interest-induced stupidity. Which is that their client can't recognize that the word estimate is a forward-looking statement. You have to explicitly say it's a forward-looking statement. And you have to include with your forward-looking statements cautionary language about where you expect the errors to be. We all know that everybody's reserve report is wrong. It's too high or too low. Hopefully we're close. And then we have Richard Feynman. And if you've never read the Cargo Cult Science lecture, you can get it off the web. It's a wonderful lecture. But he's talking about the fact that you need to explain why your conclusions, where they're possibly wrong, what's going to make them invalid, or other solutions that you can come up with. And in my over 40 years of professional practice, this is the only paper I've ever given or seen where somebody actually talked about something that didn't work. Carol Frost is still up at the University of Wyoming. I saw her on Monday. But she was trying to distinguish the, coal bed aquifers from sandstone aquifers aquifers up in the Powder River Basin. And things like salinity and pH and a bunch of other things didn't work to distinguish them. She found out that the strontium isotopes did distinguish them. But she said also what didn't work in the abstract. It's the only paper I've ever seen that actually said, we tried this and this didn't work in this case, which is something that we all need to know, that if you keep doing the same thing, it doesn't work. So getting on the models, the one thing we know about geology is heterogeneous and nonlinear. And if the math conflicts with the geology, suspects the math. All mathematicians get that. An example, I took a really nice course at Mines a few years ago on geologic data analysis. In the very first exercise, we were looking at some analyses of some granites, weathered and unweathered samples of granite, and one was a green phase and one was a red phase, doing T-tests and F-tests on them. Mathematically, you can go from weathered to unweathered, but that's a violation of the second law. So that you can't go from weathered to unweathered. And Perry Ron is an emeritus professor at South Dakota Mines, remarks, you never can validate a model, you can only invalidate it by comparison with the actual. And that gets tricky, particularly these complex models, and you're trying to build it and tweak it and make it better. Are you building your bias in there and making it look like it's a good model? Or are you really improving it? And that takes real willingness to say, where am I weak in what I'm doing? Where are my algorithms got a problem? And all these, we're all of an age, remember when you had to do all your drawings with pen and ink and doing, now we can do all these fancy models with a computer in there, color, you can rotate them, they're wonderful. Well, they're not the truth. So, the other thing you got to remember is that models evolve over time. So what was the date? Again, those of you who were taking tectonics prior to 1970 may well remember this lovely cross-section, which originally was just black and white from Marshall K about synclines, and orogenies happened. The seas went in, the seas went out, mountains came up, rode it down. And this was trying to explain what was going on with the tectonics at the time. And, it's not a bad cross-section in New England. So came along plate tectonics, which suddenly explained why a lot of these things were happening, where the depositional models are going on. And so plate tectonics has been around since the 70s. It's been improved, it's done lots of good stuff. It still doesn't explain why Colorado's so damn high. Not only the 14,000 foot peaks, but even Denver and Colorado Springs and so forth. We're high. The lowest point in the state, something like 3,800 feet, which is higher than most of the rest of the states. And changes. Here's from Silito, and the left drawing is actually variation on the old Lowell and Gilbert porphyry copper model from the 70s. Some improvements are to say, okay, we talk about these multiple intrusions that are involved in the porphyry deposits, but they aren't necessarily coaxial, if you will, which the original model sort of suggests that they are. In some cases they are, and in some cases they're not. Actually a couple of good papers in that SEG newsletter from January. Here we have the nice model for the layered igneous intrusions, the platinum deposits, and chromite and some other kinds of things that you see, still water, bushveld, and so forth. What what this model really say is that these lopolis, which is what these plutons are called, are very, very wide. Maybe a few thousand feet thick, but they're tens of miles in diameter. Nice little cartoon of the volcanogenic massive sulfide, Kid Creek and Cypress and lots of other things. One Bell Plate tectonics came along and actually got down and started building the black smokers down on these rift zones. We really understood what was going on with these depositional systems. But they produced some awful darn nice ore deposits for us. Uranium, sedimentary uranium, classic roll fronts, as well as some of the other sedimentary uranium deposits where we have uranium rich. Produce oxidized water with uranium and hitting some sort of reducing agent, precipitating the uranium. Well, the problem is that they all are based on geology, and we can't really see through rocks as much as we pretend we can. And there are uncertainties in the geology, and that's simply part of the risk. And doing the Monte Carlo or other simulations on the model, okay, you're tweaking some of the variables in the model, but you're not changing the model, so they don't really test the model per se. And, you know, tweaking and so forth doesn't necessarily help a whole lot. Back to my data analysis class, you got a set of gridded data and access to Surfer, which does contouring for you. And so the same gridded data with two different mathematical ways to contour, you come up with two different maps. And it agrees that the highest down there on the bottom, and there's, you know, a high point in the saddle, and the below is somewhere up in the top. But if you're trying to decide, you know, is this a thickness map of a manto deposit or something like that, which is right. You know, you can go play a bunch, you know, run through a different contour, but what are the contours you really like? And even if you do them by hand, we have to think about it, you know, professional judgment is required of which one you're going to use. How far are you going to push things? And then there's a lovely article by Martin Keach, a couple of years ago, getting 2.5 years ago, where he says, we got to understand what's going on in this black box in our computers. It draws these pretty pictures, and understand what the mathematical models are doing, whether it's the deterministic, you know, the inverse distance or splines, or the spatial variations of the exact Kriegian and so forth. And he came up with this lovely example. Okay, he used the same 300 data points, and here's the ordinary Kriegian. What he's trying to do is say, okay, I've got the surface of the Earth, and I've got this layer down below. This is the topography of that layer. What's the volume between the surface and this layer? So the ordinary Kriegian, he comes up with 15.5 thousand cubic kilometers. With inverse distance weighting, same data points, 15.2 thousand cubic kilometers. And then he used this radial basis function, all of a sudden we're almost at 38,000 kilometers. That's a big difference. Which of these is right? What is really going on? What do you need to know? You know, maybe this is the kind of analysis that says, we really need to know more about this. Maybe we need more than 30 data points. You know, and part of the question is, you know, what's the classic ending line to any report? We need to do further work, give me more money to collect more data. Well, there are times we need to tell our clients, we've answered the question. We could get more data and give you a more precise answer, answer, but we've got enough to answer, one way or the other. So the nice little paper by teacher, it's only 3 or 4 pages. Jim Reed, who I said some of you know, and was the technical guru behind Rockware, and writes these programs, and says, okay, we're either doing 2-dimensional or 3-dimensional things, and our computers are all these nice, neat programs, and I'll show you the program that does it, but they're not real. And here's the 2-dimensional model, which for certain, layered rocks works very well. But if you look over on the left, we've got the color-coded values in there, but each cell only gets one number. And then we see some of those cells real clearly have some variation in them. And so, the average number is all well and good, but, if you had a greater cell density, maybe you come up with different answers, but then do you have really the data to support that? And the same thing's true if you go into 3-dimensional block modeling, which is what we use for pollution plumes and ore bodies and all sorts of kind of things. The problem here is we're looking at what they call voxels, which are cubes rather than squares. Now, you've got the data, we get a nice linear diagram, let's see from the face you see there. But the fine model has 4 more cells and voxels in it, but do you really have the data density to justify that 4 cubed additional playing around? And an illustration from hydrologic modeling. The lumped model is the simplest. You need the least amount of data. And the semi-distributed models sort of an intermediate amounts of data. And the distributed models, why it's a little hard to see, but the really dense data points in that right-hand model. You got a lot more data, you get a lot more precise answer. And different modeling programs work well with each. But you got to appreciate what your model, what you do. So, again, Jim Reed, you have to be skeptical. One of the ways of checking is to draw cross sections through your models that in different directions and do all those cross sections under your data. That's the best internal check. Run X's and different directions through where you're still getting the same data honors. That's important. Of course, the problem is in between drill holes, things can happen. So you have the first rule of computing model, which is you start with a little pile of collection of data, you add a computer, and you got a big pile of garbage. That's pretty doesn't mean the pig flies. That data verification is really important as well, and Robin Smith pointed out that your field samples, you can't do anything, they are what they are, and if you don't do them right, the only way you can correct them is go back in the field. And one of the grand things that everybody says, you got to split your core. So you get duplicate samples. Doesn't work on this core. It's not uniformly distributed. Now you love the core. You wish it was your property. This is Bruce Jack up in northwestern British Columbia. 18 kilos per, to them. You know, instead of having a background of, you know, was it 8 or 9, or maybe it was 12 grams per ton of the whole deposit, and then you have these kilograms per ton. Which one's which? It's an interesting case history there. Then, you know, some of your geophysics, and we're going to have to use more geophysics and geochemistry. There's another paper in that SEG newsletter in January that's talking about the fact that the days of the old prospector and his ready ass are gone. We found this deposits with superficial expression, so we're going to have to use geochemistry and geophysics and other things to look into the ground to find our new deposits. Okay, for uranium and magnetics and a lot of other things, you need a base station to, you know, reset your equipment every day. Well, a famous case was an Australian deposit. They would use the base station that was on top of the deposit. And then they couldn't find any anomalous concentrations because they lost the base station. And one time they found somebody at the base station, another place came in and said, gee, you got a hot base station. But they actually found what was going on. Data needs to be repeatable. And again, a long time ago when I went up and down mountains, I did a lot of line miles with a magnetometer. And one place I was, I could set the magnetometer on the ground and just watch the needle go. 20 feet away, it didn't do that. Why it did it at that particular place, I have no idea. But clearly, what I had originally selected as a base station was not a good place to do it, because I couldn't get repeatability. And you know, I learned that I needed to, when I was each place I went to take a measurement, I went to say, okay, do it 2 or 3 times to see if I'm in a place that's repeatable or not repeatable, because it makes a difference. The LA abrasion test is a standard requirement for transportation departments, talking about the ability of aggregate to withstand abrasion for asphalt and concrete. He even got an ASTM number. Must be wonderful, except it's not a repeatable test. And the highway departments are now beginning to get rid of that as a requirement, because it doesn't give them a good answer to what they really want to know. You know what? How well will an aggregate deposit stand up to use on the road? Here in Colorado, we worry a lot about our snow. You know, in Denver, we're carrying water, unless you live in Douglas County or Southern Arapahoe, where you're on the well and it's going down. You know, where these measuring stations are really location dependent. You move 20 feet and you're out of the woods, out in the snow, out in the sun or the wind or something like that. You get a really different reading than if you're in the woods where it doesn't get sundown as much. So it makes a big difference. Well, we all see these. But actually, I saw this map on television last night. And this is interesting for a couple of reasons. First of all, most of the data stations are sort of along drainage divides. They're not necessarily on the divide, you know, as a statewide map, but they're fairly close. And what they're using anymore, actually, they developed pillows with measuring pressure in the pillow that they're able to convert to snow water equivalent, which is nice because then they can put them in basins they don't want to go to in the winter time because of avalanche danger and so forth, but maybe places that get lots of snow, which is why they get a lot of snow slide. But, you know, we're not, you east of the Continental Divide, you don't see any data stations. And there are a few stations off the divide down there on the San Miguel de Dolores, a couple of the Rio Grande, some of the Colorados. And not a whole lot of stations, and yet that's where we get this map we see on TV, you know, every other week or something. And they say it's the average snowfall. No, it's not the average snowfall. It says right over there on the upper, it's the median. And the median and the mode and the mean are not necessarily the same, and since this is a natural distribution, I bet they're not. I haven't gotten somebody to tell me what the skewness is. I mean, if you have a perfectly normal distribution, they're all the same, but really it's a median, which is, okay, is it, the median's the difference between high and low point, and maybe for snow forecasting, that's a number that's useful, assuming, given that the median and the mean may be different.
You mean there are no stations in the southeast part of the state?
No. And I've seen a couple of papers that say one of the problems of our estimates is that we don't pay enough attention to the lower parts of the basin. Where there does, snow comes in, it can be there, it can melt away, and so forth, but this can make a difference. And remember 1983, the hell was it snowy, and there was no spring. And June came and it suddenly became summer. And the water started flowing out of the mountains. Salt Lake sandbagged its major downtown streets into canals. And the Glen Canyon, the Bureau of Reclamation has a schizophrenic assignment. They're supposed to store as much water as they can against drought, and they're supposed to lower the reservoirs so they can catch the floods. So they were trying to open the spillway at Grand Canyon and realized that the natural cavitation you get in tunnels was sort of destroying the tunnel, particularly when you got a weak rock like Navajo sandstone, which is what the dam's in. They actually welded angle iron onto the top of some of the spillway gates and bolted 4x8 sheets of plywood to help sort of artificially raise the level of Lake Powell 4 feet. So that they damn near lost Grand Canyon. There's a wonderful book called The Emerald Mile that's about running through the river path. Lots of things, but it talks about the problems the Bureau of Reclamation has. One book about how they damn near lost the dam.
So that accuracy you see there, where there's no measuring, but it says 131%.
Yeah.
Not 100%, not 150%.
Well,
131%.
Yeah. Percent of the median. And they also only count stations for which they have 30 years of data. And so, by having that many years of data, and then also the subsequent stream flow in the summers, you can sort of say, okay, so many, measurement of snow water equivalent of whatever the amount is here at this station helps me come up with what it is. It's sort of a data fit exercise. We all want to know what this snowpack is. But what's the data really behind it? As I start looking a little bit.
Well, I think the question maybe is significant figures without data points. Yeah. That's kind of amazing.
It's like you see in bird resources there at second decimal place. 0.28 grams per tonne in per. That's a wild ass guess.
Yep. The nice thing about these pressure pillows is that you pull a lot more out, and get to them with satellite-based telemetry.
But this means you would just shut down all the river rafting on the Arkansas, right? That's what if you read that data correctly.
No.
There's no data to say there's any water in the Arkansas.
Well, there's actually some that are on the some of them that are on the Arkansas side of the ridge, but there's not a whole lot. And so you, maybe if you're an Arkansas rafting company, you say, we need some more data points. Instead of just one or two of the collegiates and a couple up by Leadville. Anyway, so George Bach said, if, no need to ask if a model is true as if you mean, is it really true, because it's not. The question is it illuminating and useful, or the short thing is, all models are wrong, some are useful. So, one of the things that, of late, the weather people have been showing us the European and American models of predicted hurricane tracks, which is, I think, a real improvement for them. They say, we really don't know, here are two places that it might go. Well, this is actually a map from the University of Wisconsin-Madison. Is one of these places that studies hurricanes. It's like the annual hurricane prediction, how many storms are going to get, comes from Fort Collins. Hey, wherever. So here are a dozen or so hurricane prediction tracks for this tropical storm, Bonnie. And most of them say, okay, it's going to come on shore, and it's either going to be a little bit inland or sort of close to shore and head off to the mid-Atlantic. Except for these two, the one headed for Lake Huron and the other headed for northern Quebec. Now, I'm going to assume that, each of those, all of those models were developed and have some reasonable utility, or they wouldn't use them at all. So why are there these two outliers? Why are those two so crazy? Now, if you look at the orange one that goes up to Lake Huron, it actually is with the rest of them for the first few days, until it suddenly takes this hard left turn and heads north, or west-northwest.
How wide is it? It might both be right. It's a hurricane.
Well, since this was a tropical storm, well, got a point, but anyway. The point is that the variation and letting people know is more truthful. And here are the global climate change people. This is from a national report from 2017, and depending on which parameters you use, we're in deep trouble or not. At 2020, we're still not in a place where we decide which one's which. You gotta remember that Ed Lorenz, who came up with the butterfly effect, was a meteorologist. He came up with that because he was looking at meteorological data and found out about chaos theory. Anyway, people are, we're going to be, 5 degrees, 10 degrees too high by the end of the century. Well, depends on which model you use. So, what are you going to use the model for? Your early models are not as detailed. As like, when you first come out and looking at the deposit, and getting a couple of grab samples to give you an idea of what the grade range is in there. It isn't, statistically valid as a sampling, but if the grab samples aren't any good, you're not going to go back. That's why when I was at the commission, this is what we had to do. We didn't have the budget to do a lot of drilling and sampling, so we get the people to tell, where's your very best stuff? And we hydrate it. And when it came back 0, we could find these. Knowing the area you're dealing with and the play, the kind of deposit you're working with, of course, makes a big difference in how you do things. You got to incorporate all your data that, if there's some reason for saying this data point is invalid, of course, you can get rid of it, but just because it's an outlier, you can't ignore it. That Bruce Jack example. Usually, if you get, start at the bigger scale and come down, it's easier. and scale makes a huge difference when you're looking at something. You start with the structural stuff, all the big things. Then, usually Occam's razor works. If not, why you need to explain why. Reconciling your frames, same thing Jim Reed was talking about. So, models can be useful, they're not the truth. They must start with the data. Keep it simple usually. You've got to use professional judgment. Don't fool yourself. You're too witted to it because you're selling a pretty picture. And, identify and disclose all the reasons why your estimate is going to be wrong, because it is. Thank you. Yeah.
Can you go back to that last slide? I guess I'm kind of taken back with it. Gee, I read a lot of these things and I don't see a lot of description of what is wrong.
No, and this is why you need to pay attention to 27A of the 33 Act, Safe Harbor.
Exactly.
Yeah.
Bill and I both have spent the last few years over at the School of Mines with seniors in mining. They have to do a feasibility study on a real deposit. And all of them, as long as I've been over there, which is 8 or 10 years, they do it with computers. And they understand that it comes out of the computer, it's got to be right. And one of the things that it's bothered me a lot, and I preach to them, draw some cross-sections of your computer model and see from the real data and see if it compares to that computer data. But I think what's happening is everybody in this room that had to do that when they were in college did it with colored pencils and a slide rule, yeah, but they did it by hand. And when they got through, they may not have been right about their model, but they understood what that model looked like that they designed the mine plan for. Yeah. And I think the kids today haven't got a friggin' clue of what it looks like because they put it in XYZ model and it burps out a little pretty figure on the screen and a tonnage and grade. But when they go to mine, if they have to go mine that model, they will learn it in no nice little blurb and the tonnage and grade's all.
Exactly.
But they don't check themselves and they don't think to check themselves. And that's going to leave our people in the future that's got to go do that to make a lot more errors than we all made, and we made enough.
Well, I think the basis for this talk and this preparation was primarily for going to schools.
Well, it's a good one to go to school.
And,
but you're over most of them's heads. You got to bring it down a little bit.
Well, Wyoming on Monday was observed first time. So they have a seminar program every week, and I was the first non-academic that they ever had talked about that seminar program. And they realized that I was providing them with some really useful information that they needed to know. And I was with one of the professors who was doing various sorts of resource estimating. I said, you should ban the word reserve, resource, and ore from your vocabulary. That way you won't get sued. We can talk about deposits, we can talk about occurrences, whatever's appropriate for whatever you happen to be looking at. I suppose what the final slide should quote 10b5 from the 34 Act about false and misleading information, and you can get sued.
Harry made a very important point there. Don't fool yourself.
Yeah, that's it.
Yeah.
Don't fool yourself.
You know, about 30 years ago, A&I Rural from Australia said we can build a better sag mill than those Alice Chalmers guys and the Nordberg guys over there in Milwaukee, right? So they said we can just make that a flat plate, we'll do a weld here between the head and the shell, and our finite element model, it shows it's all going to be honky-dory, it's all going to be good. So they built a number of these mills. And all of a sudden, within about 2 years of operations, around the world, people started noticing there's moisture coming through the joint. A couple of mills fell off the pedestal. And it nearly broke the company because they had to figure out how do we fix this. And it was quite inherent flaw all the way through. But everybody trusted the model. Computers said the boundary conditions were, and it's all good.
Yeah.
I think the other problem there is engineering. They really fine-tune the models, because I know on like a lot of mills, they build them like bicycles. Like double-bladed tubes, make it nice and thin, because the model tells them they can do it, and then they fail. Yeah, one more question for Dave.
I can stick around, but
Dave, you always got really interesting slides and interesting material. We appreciate it very much, but I'm going to thank you again for all the hard work on the international standard thing, because I don't know how many conversations we've had right in this room about why in the hell does the United States have one set and the rest of the world has a whole different way of looking at these things. And we finally won at least a small battle. Now we have to implement it.
well, one of the things that Bob Cameron and I were discussing not too many years ago is, Industry Guide 7's really not all that bad.
No, it's not.
We got the best definition of reserves, because instead of worrying about all this pie and this pie stuff,
Exactly.
we're talking about what pays the bills. What can you recover out of it, and that really is a vital thing.
But credit to you, you really built that Guide 7, and then you said,
No, I didn't. I
Well,
did a couple of things, so I unfortunately.
you've commented on many, many times. So.
The measures indicated that there was a mistake, but it's what I'm kept busy on working up this presentation for what the new rules are, and one of the things I've done is gone through and talked about, I want to pay attention to the Securities Act and regulation. You got to remember that these are little gotchas that aren't in the rule you're paying most attention to.
Well, all those reports that Paul was talking about, almost in conclusion, at least half of them, they'll say, and we had our reserve model indicated we had so much reserve. And then Paul and I tear the report up and say, you don't report any reserves. You don't have the requisite experience to be doing that. And the light finally goes on with most of them. So, again, thank you very much.
Very good.